In problem 4, we're considering a best of 5 series. And a best of 5 series is a competition between two teams where a team will win the series by winning 3 games in the series. As soon as one of the teams wins any of the 3 games, the following games are no longer played. So the outcome of a best of 5 series is defined by the results of each game. For example, and this is from one team's perspective, so for example, the Golden Bears. So they may win 3 in a row, they may win 2, lose 1, then win a third. They may win, lose, win, win, or they could have a pattern of win, lose, win. And these are all different winning outcomes for a particular team. So now we have 2 basketball teams, the California Golden Bears and the Stanford Cardinals, which are going to play a best of 5 series. And we're going to analyze the situation. Part 1 asks us how many possible outcomes are there for the Golden Bears to win the series with exactly 3 wins and 2 losses. So for them to play 5 games, we know that they have to have won their 5th game. Also, because for them to play 5 games and win the series, they have to win the 5th game. So we have 1, 2, 3, 4, and then a win. Now, of the remaining 4, we need to choose 2, which will be losses. Alternatively, we can think of it as choosing 2, which will be wins. So we have 4 slots, choosing 2 options for arranging WWLL in these 4 slots. So 4 choose 2 is 6. There are 6 possible outcomes for the Bears to win the series with exactly 3 wins and 2 losses. Now we want to look at a more general question of how many outcomes there are for the Golden Bears winning the series as a whole. So we already looked at the 3 win, 2 loss case, and we said that that was going to be 4 choose 2, which is equal to 6. But there's also the case in which they have 3 wins and 1 loss. So for example, here we have 3 slots and then they have to win the last game, because otherwise if they had won, for example, the 3rd game, then it would have been 3 wins and 0 losses. So now we have 3 slots and we want to choose one of them to be a loss. We could also have looked at this as 3 choose 2, and we're choosing 2 of the slots to be wins. But if you look at the formula for choose, these are actually both equal to 3 factorial over 1 factorial times 2 factorial. And so this will be equal to 3. Then we also have the 3 win, 0 loss case, but this is just win, 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 and there's only 1 of these. So in total we have 6 plus 3 plus 1 equals 10 different outcomes for the Bears winning the series. For part 3, we want to calculate this formula explicitly using explicit calculations. And we're going to do this using induction. We're going to show that the sum from I equals 0 to k of n plus I, choose I, is equal to n plus k plus I, choose k. And this part here is just the first k terms of the sum. So our base case is k equals 0. In this case, we have the sum from I equals 0 to 0 of n plus I, choose I, which is equal to n, choose 0, which is equal to 1, which we can also write as n plus 0 plus 1, choose 0, which is n plus k plus 1, choose k. So it works for our base case. Our inductive hypothesis will be that the sum from I equals 0 to k of n plus I, choose I, is equal to n plus k plus 1, choose k for all k between 0 and n. So now our inductive step will be to write this out for k plus 1. So we have that the sum from I equals 0 to k plus 1 of n plus I, choose I, is equal to, and we can take just the first k term, so I equals 0 to k of n plus I, choose I, and then we add on the k plus 1 term. So n plus k plus 1, choose k plus 1. So this is just splitting up the summation. And by our inductive hypothesis, we can write this piece here, the summation, as n plus k plus 1, choose k. And then we just rewrite this, or keep this part from the previous line, k plus 1. Now if we write out the formula for choose, we end up with n plus k plus 1 factorial over k factorial times n plus 1 factorial plus n plus k plus 1 factorial over k plus 1 factorial n factorial. Now, we can notice that there are a couple of common terms here. So for example, each of them has an n plus k plus 1 factorial. Each of them also has a k factorial. This k plus 1 factorial is k plus 1 times k factorial. And similarly, they each have an n factorial, because this n plus 1 factorial is n plus 1 times n factorial. So now this leaves us with this. If we combine these fractions, we get, again, this part comes down here and stays the same, over k factorial, n factorial. Now we combine these fractions, and we get n plus 1 plus k plus 1 over n plus 1 times k plus 1. And then we notice that this here is actually n plus k plus 2, so that can combine with this n plus k plus 1 factorial to become n plus k plus 2 factorial. We similarly take the n plus 1, combine it with the n factorial, and turn that into n plus 1 factorial, and the k plus 1 combines with the k factorial to be k plus 1 factorial. And then we look and we notice that this is actually the formula for n plus k plus 2, choose k plus 1. So now we've shown that the sum of the first k terms in this summation is n plus k plus 2, choose k plus 1. Now if we let k equal to n, then we know that the sum, sorry, I misspoke. We've shown our inductive hypothesis, and so yeah. So now we plug in from I equals 0 to n of n plus I, choose I, is equal to n plus 1, choose n. This is equal to 2n plus 1, choose n. But remember with the choose, when we have, for example, a plus b, choose b, this is equal to a plus b, choose a. So you can actually write this as 2n plus 1, choose n plus 1. And now we have shown what we set out to show. In part 4, we want to look at the number of outcomes available for the bears to win the series if it's a best of 2n plus 1 series. So in a best of 2n plus 1, we need n plus 1 wins. So this could mean, for example, n plus 1 wins, 0 losses, and there's one such event. We could also have n plus 1 wins and 1 loss. And in this case, there are n plus 1 choose 1 events. So remember that although they'll play n plus 2 games, we know that the last game has to be a win. So that's why we have n plus 1 choose 1. We can also have n plus 1 wins and 2 losses. In this case, we have n plus 2 choose 2 such outcomes. And for example, this goes on all the way until we have n plus 1 wins and n losses, in which case we have n plus n choose n is equal to 2n choose n outcomes. So now if we simply add up the total number of outcomes, and let's just cleverly re-express this 1 as n choose 0. So now we have the total number of outcomes is equal to n choose 0, so 0, plus n plus 1 choose 1, plus n plus 2 choose 2, and all the way up to 2n choose n. This looks suspiciously like the summation from part 3, and in fact we can write it like that: I equals 0 to n of n plus I choose I, and we know that this is equal to 2n plus 1 choose n plus 1 given the previous part, and therefore we're done. In part 5, we essentially want to explain the result that we got in part 4, but more intuitively, without calculations and without using this without using the result from part 3. So if we think of the tournament as not stopping when someone gets n plus 1 wins, but instead as them having lost all of their subsequent games, then we can say that there are 2n plus 1 choose n plus 1 ways that there are n plus 1 wins by the Bears. So this is kind of a new scenario. The old scenario is that they just stop after they get their n plus 1 wins. But we know that we can actually find a one-to-one mapping between this old scenario and this new scenario, because I can tell you, okay, as soon as the tournament stops, put the winner down for losses for the remainder of the tournament. And vice versa, if I have a situation in which someone has lost for the last K games of the tournament, then I know that they won in the first part of the tournament. So now I've created a bijection between these two sets, which means that they're exactly the same size. So that means that there are 2n plus 1, choose n plus 1 ways for the Bears to win the series. Bijections are very useful. Part 6 is actually basically the same as part 5, in which we have a best of n plus 1, n plus 2, minus 1 series, where the Golden Bears win the series by winning n1 games in the series, and the Cardinals win the series if they win n2 games in the series. And so for the same reasons as in part 5, we have n plus 1 plus we have n1 plus n2 minus 1 choose n1 ways for the Golden Bears to win the series. So now we're going to go into the probability part of this, and for example, we're going to look at the case where the Bears have a 0.7 probability of winning each game if the game is played. So we want to know what the probability is that the Bears win the series with exactly 3 wins and 2 losses. So we know from the first part that there are 6 such outcomes, and now we just need to figure out what the probability of each outcome is. So, for example, the probability of a win, win, loss, loss, win. Keep in mind that the fifth game always has to be a win so that they will play 5 games. Then we have 0.7 times 0.7 times 0.3 times 0.3 times 0.7, which is 0.7 to the 3 times 0.3 squared. We could have also had maybe win, loss, win, loss, win. And in this case, we're also going to have 0.7 cubed, 1 for each win. So this gives us 0.7 cubed, and for each of the losses, we're going to have 0.3 squared. So we see that no matter what order these wins and losses come in, we're going to have a 0.7 to the 3 times 0.3 squared probability of each one. So therefore, the total probability is 0.6 times 0.7 cubed times 0.3 squared, which turns out to be approximately 0.185. So part 8 is kind of like a combination between part 2 and part 7. So we still have that the probability that the bearers win the series is the probability that they have, for example, 3 wins, 0 losses, plus the probability that they have 3 wins, 1 loss, plus the probability that they have 3 wins, 2 losses. And I didn't write it, but we're also, this is the probability that they win the series and have 3 wins, 0 losses, for example. So to have 3 wins and 0 losses, this is going to be 0.7 cubed because they have to win all 3 of their games. We saw from the previous question that this will be 4 choose 2 times 0.7 cubed times 0.3 squared. And by similar logic to part 7, this part here will be 3 choose 1 times 0.7 cubed times 0.3. So when we add all of these guys together, what we get is approximately 0.837. In part 9, the captain of the Cardinals proposes to change from a best of 5 series to a best of 3 series, and basically the question is, should the Bears accept this? So what we want to know is the probability of the Bears winning in a best of 3 match versus the probability of the Bears winning in a best of 5 match, given that they have a probability 0.7 of winning each particular game. So we know from the previous part that the probability of Bears winning best of 5 is about 0.837. And now we want to look at the probability that the Bears win best of 3 series. So this is going to be the probability that they have 2 wins, 0 losses, plus the probability that they have 2 wins and 1 loss. And by exactly the same logic from the previous questions, this will be 1 choose 0, which is 1, times 0.7 cubed. And this will be 2 choose 1 times 0.3 times 0.7 squared. And this is following exactly the same logic from the previous parts of this problem. So now when we add these guys together, what we end up with is 0.784. So if the Bears accept the switch to a best of 3, they'll have a 0.784 chance probability of winning the series, as opposed to a 0.837 probability of winning a best of 5 series. So this gives an advantage to the Cardinals, and the Bears should not accept this request. So now we're going to quickly look at some conditional probabilities. We're still going to assume that the Bears have a 0.7 probability of winning each game if the game is played. So for example, in part 10, we want to know the probability that the Bears win the series given that the Bears win their first game. So I've written down in the corner this very handy definition of conditional probability that says that the probability of A given B is equal to the probability of A and B happening divided by the probability of B. So, using this, we know that this is equivalent to the probability of Bears win the series and the Bears win their first game divided by the probability that the Bears win their first game. So winning their first game is a 0.7 probability, the same as winning any other game. So this right here is 0.7. Now what's the probability of the Bears winning the series and winning their first game? So for this piece right here, we know, for example, that they could win all 3 of their games. So we have 0.7 cubed. Or they could lose 1 game. So now we have 2 choose 1 times 0.3 times 0.7 cubed. So notice in previous iterations, this was 3 choose 1. So we had 4 games. The last one was fixed as a win, and the other 3 were free to be wins or losses as we wanted. However, we've now also fixed the first game. So we know that it has to be win, something, something, win. And then we have to choose one of these to be a win and one of these to be a loss. We only have 2 free slots, so that's why it's 2 choose 1. Then similarly, we have 3 choose 2 times 0.3 squared, 0.7 cubed. So once we evaluate, well, this piece right here is about 0.641. So then the whole probability is equal to 0.641 divided 0.7, which is about 0.92. So that's the probability that the Bears win the series given that the Bears won their first game. Now we want to know, in part 11, the probability that the Bears win or won their first game given that the Bears win the series. So using the same formula from before, we know that this is equal to the probability that the Bears win their first game and Bears win the series divided by the probability that Bears win the series. So we know from the last part that this here is equal to 0.641, and we know from part 8 that this is 0.837. So the whole thing is equal to 0.766. So in part 12, we want to know the probability that the Bears win their 5th game. This is a little bit deceptive because we actually want to know the probability that the Bears win their 5th game and the 5th game was played, because it's not guaranteed that the 5th game is played. If they play a 5th game, the probability of winning that particular game is 0.7, but we don't know for sure that they play 5 games. So we need to actually evaluate the probability that they win the 5th game and 5 games are played. So we can rearrange this formula from before, and we see that the probability of this will be the probability that the Bears win their 5th game given that the 5th game was played times the probability that the 5th game was played. So if they play 5 games, the probability that they win is 0.7, as mentioned earlier. So now we need to know the probability that the fifth game is played. So the probability that the fifth game is played means that there were 2 wins and 2 losses prior. Which means that we have 4 choose 2 times 0.3 squared times 0.7 squared. So once we multiply these all together, we end up with this being about 0.185 is the probability that they win the fifth game. From part 13, we want to know the probability that the Bears win the series, given that the Bears win the fifth game. Now, we can actually just argue this in words, and it's probability 1, because if we get to the fifth game, it's sudden death, meaning that there have been 2 wins and 2 losses up to this point. So whoever wins the fifth game wins the series. If the Bears win the fifth game, the Bears win the series. So given that they won the fifth game, the Bears win the series with probability 1. And finally, for part 14, we want to know the probability that the Bears win the fifth game, given that the Bears win the series. Now, we can't argue that this will be 1, as we did in the previous part, because we don't know that they necessarily play the fifth game. So this is equal, again by the equality down below, to the probability that the Bears win the fifth game and the Bears win the series, divided by the probability that the Bears win the series. So we know that this is going to be 0.837 by part 8, and we know that this will be 0.185 by previous parts, so the whole thing is 0.221 probability that the Bears win their fifth game, given that the Bears won the series.